I think our field really need a lot more entrepreneurs to kind of innovate, disrupt the current state of approaches in oral health. And what we do in our center, we actually focus in 3 different disciplines of engineering, material and computational sciences. And of course, that in collaboration with the dental medicine faculty, we have 2 goals. One is to study oral disease mechanisms and craniofacial disorders, including oral cancer. We have here Ray, who helps to kind of spearhead oral cancer part. And also creating, affordable and low-cost therapies and devices, because I think that's a big challenge that we face, and how we come up with the new ways to treat or prevent. But I think this needs to be affordable, needs to be low cost, that can be, brought to everyone. And obviously, working in precision diagnostics, and we are collectively working on these 2 areas. And more excitingly, I think, is we are also building a community of really the next generation scientists, and we are very excited and very thankful for the support of NIDCR, work with NIDCR, and also with Colgate to train this next generation dentists and scientists and engineers to really work together. And we have an incredible diverse group of amazing young talents. We have chemical engineers, we have roboticists, we have microbiologists, clinicians, and including 2 who are very interested in entrepreneurship, which are very excited. And again, entrepreneurs are needed in our area. And what we are hoping with this training program is that we will create this new workforce where, working across or at the interface of disciplines is not something unique, but rather a norm. Because I think in terms of future, really working at the interface is critical for us to advance our field. So what we have now is this really a community of faculty, mentors, and trainees trying to leverage all these engineering approaches that can, I think, really advance big time oral health innovations. And I think, now is really a great time to be at this interface. We have this really rapidly evolving technologies just are begging to be, leveraged to tackle the difficult questions, the difficult issues we have in oral craniofacial healthcare. And who will benefit the most of this multidisciplinarity of this amazing time that we live in, where we have all this technology that can help? I think are the trainees. Are the next gen scientists who can really benefit from this. Again, as I mentioned earlier, it's a really great time to be a scientist. Really leveraging all these interesting and really applicable technologies to help advance, both understanding of the disease mechanisms, but also coming up with better ways to prevent, diagnose, and treat. And just give you some examples. For example, Yuan Lu, who's really a bright clinician scientist, who is developing these low-cost, anti-caries nanoparticles that are really tailored for children with iron deficiency, who in turn, are more susceptible for dental caries. It's a very neat nanotechnology where these nanoparticles can bind to specific pathogens, but not to the commensal microbes, and can be effective in killing them without disturbing the oral microbiota. And she was recently awarded the Women's Science Award, which was awesome for her. And now she's on her way to become a faculty member and hopefully push this technology and more during her career development. And we also have Marshall Padilla, who is part of this great ADOCR Mind the Future program. If you're not familiar, please, I think tomorrow there will be a session on this. It's a great program that help to create this highly inclusive network of different scientists and helping each other to build up their careers. What Marshall is doing is something really cool, in my opinion. So they are working with lipid nanoparticles and also with mRNA technology. He's working with Mike Mitchell and Drew Weissman. And as you know, Drew was one of the Nobel Prize winners in medicine this year. We're super excited about him, and Kathleen Carrico winning. So now he's leveraging this mRNA technology and lipid nanoparticles to treat craniofacial disorders and organ cancers. So I think Marshall has some very interesting and very exciting work ahead of him, and really excited about what he'll bring to our field. And we have Z Ren, who just presented today in the oral session. He's going to present tomorrow. And what he found was this very interesting bacterial fungal assemblages in saliva of diseased children. And what was very unique about this bacterial fungal assemblage, these are floating saliva. And once they are bound or colonized on the tooth surface, they develop this incredible surface mobility. Something that, that the microbial world has not seen before. It's almost like a higher organism type of a mobility, looking almost like one of those invertebrates, jumping, right, from one place to another. And that really grabbed a lot of attention, not only in our field, but also in microbiology. It caught up the attention of Scientific American, who wrote a very nice article about, this kind of, they call it walking dental, but this mobility property that Z helped uncover, during his training. So, all this, I think, really illustrates, the importance of working in team, working with different disciplines together. And I just want to close with one last story that, what happened when we have roboticists, a dentist, and chemical engineers sitting at the same table, just talking with each other, and start to collaborate. Now, what they come up with micro robots, something that we thought was a science fiction not long ago, and micro robots that can be used against biofilm infections. Here we just show, they are able to 3D print or using 3D molds to make this tiny, super miniature helicoid robots that can go inside the root canal. And here, seeing is believing, and able to control this micro-sized robot inside the tooth canal, right? So these are the little robots go inside the tooth canal. Now you can imagine the possibilities to really precisely guiding them to the apical region and delivering drugs, for example, to not only kill biofilms, but also help to heal the tissue around that region, right? Something that I think is very exciting, that I think is only possible, again, when you bring different way of thinking, different disciplines together. And more recently, they moved on to more clinical scenarios where they're able to control these micro robots inside the actual tooth in a mini pig model, where they're able to use just like everyday equipment in the clinic, a CBCT, able to track the robots. Here they are deployed in the popo cavity, and then just bringing and tracking them all the way down to the apical area where there will be, for example, delivering drugs, etc. I think this can be a very transformative technology for the future. So in the end, again, I think really the multidisciplinarity really goes hand in hand with team science. You cannot do things alone, especially nowadays. We have so many disciplines impacting each other, converging to each other. It's really highly synergistic. It's highly interactive, collaborative, that helps to tackle big questions. And I think really brings the best of it, right? To not only collaborate, but also to think bigger, to really go after higher, big impact, big dreams in terms of dissecting disease mechanisms and finding new solutions. And I'm just going to end with 3 quotes that I think, in my view, brings the concept of team science from 3 totally different background, people with different background. The first from a poet, a writer, who said, Individually, we are one drop, but together we are an ocean. Very simple, but very powerful quote that kind of illustrates the importance of team science. And our beloved Phil Jackson, probably one of the best coaches out there. It's a very famous quote from him: "The strength of the team is each individual member. The strength of each member is the team." It could not be more true and applied to team science. And finally, our favorite, evolutionary biologist: those who learn to collaborate and improvise most effectively have prevailed. And I think this will hold true moving forward as well, especially as I mentioned, all these different technologies, disciplines converging, into a single unit. So we really need to learn how to work together and collaborate. So with that, if you guys are interested in learning a little bit more what our center is doing, our training program, there's a QR code right there. Just feel free to take a look and visit. We're happy to answer any more questions. And please check out this new, a very recently published perspective article that I put together with Kate and JDR, really bringing this perspective of the importance of the bringing together dental medicine engineering to really advance oral health innovations. So there's a QR code. Feel free to take a look, and I'm happy to answer any questions. So thank you.
Are there any questions for Dr. Koo? Could probably have time to take a question or two.
I think Puting, is that correct, your name?
Yes, I don't have any question. I just think your presentation is great. Yes, I learned so much from your presentation. Thank you.
Well, if there are no questions, we could move to Dr. David Kohn.
I have one quick question. If you
Oh,
don't
yeah,
mind.
please.
Okay, thanks, Dr. Koo, for the wonderful talk. Just have a quick question. So in your opinion, what's the most challenging or most difficult thing in research collaboration? And what are your suggestions for like young investigators? Thank you.
Yeah, I think the most difficult, I would say most difficult, I would say the most challenging is that, you need to understand who is or who are in the other side of the table, right? So that's what I think, training programs where you bring trainees like you yourselves, learning how to communicate, talk with others in the different disciplines is important, right? I think the biggest challenge is the communication. How you communicate your problem, your issue you want to address using different disciplines to the other side of the table, right? I think communication, in the understanding the vocabulary, the language, of your future collaborator in a very different discipline. I think that is one challenge. I wouldn't say the big challenge, it's one challenge, how to learn to communicate and really put out what your big question or big challenge is to get the maximum help you can get from others. So I think that would be one example, and I think in one way to help address that is really exposing yourself as much through the training program or through really being curious to reach out to other disciplines. So you start to develop your interactive language very early on in your training career. So that'll be just my 2 cents.
Thank you so much.
Thank you.
Okay, thanks, everybody. Thanks, Lynn, for inviting me. My message is very similar to Michel's, just with different examples. So I'm Dave Kohn. I'm a professor in both the dental school and biomedical engineering at Michigan, and also the director of the Michigan-Pittsburgh Weiss Regenerative Medicine Resource Center, which is one of 2 national resource centers that are part of the NIDCR doc track program. So what I want to talk about today is a little bit about my journey, how I got to where I'm at today. Talk about the programs and teams that I lead, how I evolved into them, but spend a chunk of the time talking about team building and view that through 3 lenses. One is building a team within your lab. The second is building a team across labs. And the third is building large programs like the programs that Michel spoke about. Some do's and don'ts and lessons learned in team building, and save plenty of time for Q&A. So my journey, I've had the phenotype of a researcher and a professor since I was about 5 years old. In kindergarten, the teacher had a rule: you had to leave 1 block of each type in its appropriate cubby space. So you'd remember that the square block went back to cubby number 3. And at 5 years old, I said, I don't like this rule. Why do I have to be regressed to the mean when I know that the square block goes in cubby number 3? So I lobbied the teacher to let me take all the blocks out of cubby 3. So at 5 years old, I had the phenotype of a researcher and someone that didn't want to toe the line. A couple of years later, I was about 8 years old. I broke my arm playing football, and I first got interested in bones. The x-rays were cool, the cast saw was cool, but the doctor, the orthopedic surgeon, put a cast between my thumb and my index finger, and my mother said, it looks too tight. And the orthopedic surgeon got on his high horse and said, I'm an orthopedic surgeon, blah, blah, blah. Well, the next day it's all discolored. So we went back, and the next resident said, oh, no, the cast is too tight, no problem. So 8-year-old Dave saying, my mother seems to know more than the surgeon. The bones are really cool, but I don't want to become a surgeon. So in high school, 1977, my high school biology teacher said, those of you that like this class and are good in math, think about something called biomedical engineering. That's the first that I ever heard of biomedical engineering. He also said something really profound that stuck with me to this day. He said, you may not get the credit of the surgeon, but you're at the beginning of the conception of the product, and the surgeon is at the end. But you can have more impact at the beginning because you're designing something that 1,000 surgeons can use. So that's how I got into biomedical engineering, just seems something cool. And then as an undergrad at Tulane University, in the late Steve Cowan's biomechanics class, we had a supplemental book that's still on my shelf. And I won points by talking to him about this a non-required reading, and he offered me a position in his lab as an undergrad. My first publication was in the Journal of Biomechanics. I had an abstract at the ORS meeting in the early 1980s, and these catapulted me to grad school in bioengineering at the University of Pennsylvania. From there, I had some papers. I had some, my first patent was from work I did at Penn. I was ultimately licensed to Depew. So a couple of things happened out of this graduate research. One was it was my first relationship with translational research, which is carried forward to this day. The other was the program chair of the Society for Biomaterials meeting. The year I was finishing was Bob Craig from the dental school at Michigan. He saw my papers. He sent Paul Duchenne, my PhD advisor at Penn, an ad that Michigan was looking for positions in the dental school. So Paul gave it to me, and he said, this is a good position. You should look into it. I said, Michigan? It's one of those M states in flyover country, isn't it? And he gave me what I call the life cereal talk. Try it, you'll like it. So I tried it and I liked it. And 33 years later, I'm still at Michigan. So it was that encouragement, the start of the creation of a network, and that got me into dental research and the position I'm still at today. So my lab in Michigan is based on understanding skeletal structure and function and causes of fragility, and then regenerating the skeletal system. And it's two pathways. One is top-down, extracting structure function information from tissues. The other is more bottom-up, using that information to design materials. And a large portion of this has a footprint in the mission of the NIDCR. It's both in the NIAMS and NIDCR missions, and we've had a lot of multidisciplinary collaborations and trainees through the years. Non-inclusive list of collaborators, some 20-year collaborations, other one-off, but the message is same as Michel gave. Interdisciplinary collaborators make the research elevated, make it more exciting, and you learn from one another, the people that you might not have the same background as. So beyond my lab, I run 3 large regenerative medicine programs at Michigan. All of these are at the interface between dentistry and engineering and medicine. The first is our longstanding T32. This going long before I ever thought about Michigan. This was a great synergy between dentistry and what was then the metallurgy department. As tissue engineering evolved, this became more of an interaction between dentistry and biomedical engineering. The second program is the Michigan Pittsburgh Weiss Regenerative Medicine Center as part of the DocTrack program. We probably have 100 faculty, trainees, staff, third-party experts that help guide research projects through the translational funnel. And the third program is one of the university's biosciences programs funded by the president and the provost. We have about 100 faculty involved in that with a focus on programmable biomaterials for regenerative medicine. This takes many of the elements from the dental, oral, and craniofacial NIH Center and makes them more campus-wide and more regenerative medicine wide. So a little bit about this Regenerative Medicine Resource Center. It's a multidisciplinary team, and in addition to the academic experts from dentistry, from engineering, from the life sciences, it also includes non-academic experts from the regulatory sector, from the marketing sector, from the commercialization sector. So this is really team science on steroids, how to take academic projects and guide them to translation, both through the FDA and to commercialize them for ultimate clinical adoption. So we support, this is a national center, we support the regenerative medicine community by providing the expertise and the resources to shepherd technologies through preclinical studies through the FDA. And a big component of this is also education, because it really takes a traditional academician, they need to shift gears and put on a very different hat to truly do translational research. So this is part of close to a 10-year program that I've been running since the beginning in 2016. We are probably halfway through the 3rd stage and looking at what's going to come next, which is really having projects exit to clinical adoption and the marketplace. And the power of team science is shown here in that just about all of our project teams have their IP in place. almost 2/3 have had some form of FDA interactions, if not a formal filing. And the teams have been able to generate a large number of follow-on funding and commercialization activities. So that's, I think, the impact of team science. Again, the teams here are not just traditional academic multidisciplinary teams, but cover non-academic and non-scientific sectors. Okay. So I want to spend some time on team building, and a typical academic portfolio can be viewed as this stool: research, teaching, service, and perhaps a fourth leg of clinical care for those of you that are clinician scientists. And the best advice I was ever given was when I started at Michigan, the ideal split was 50% of your effort should be developing your lab, another 25% should be collaborative research, and another last 25% teaching, service, clinical care. When those ratios get out of whack, that's when problems arise. So collaborative research is great. That's certainly been the mantra of this session, but don't do it to the extent that it compromises you evolving the core of your lab. It should ideally be part of the evolution of your core. Okay. So start by thinking about, how do I build the team in my lab? Well, it's really what your vision is, and then ensuring that you have the time, the resources, the space, and the people that are going to enable you to execute that vision. And some more personal situations are: how big do I want my lab? What's the phenotype of the students? If you want to recreate a program like Michel, then you're looking at multiple phenotypes. So what's the phenotype of the people that are going to enable you to execute your vision? And then what's the cost of doing business? What's the cost of having trainees in your lab? Even with a T32, there's a large cost-sharing element that has to be taken up by non-federal funds. Okay. So I think building your lab should be the 50% of your effort that is dedicated towards building the core of your niche.